Swarm intelligence is the collective behavior of decentralized, self-organized systems, natural or artificial. The concept is employed in work on artificial intelligence. The expression was introduced by Gerardo Beni and Jing Wang in 1989, in the context of cellular robotic systems. SI systems consist typically of a population of simple agents or boids interacting locally with one another and with their environment. The inspiration often comes from nature, especially biological systems. The agents follow very simple rules, and although there is no centralized control structure dictating how individual agents should behave, local, and to a certain degree random, interactions between such agents lead to the emergence of intelligent global behavior, unknown to the individual agents. Examples of swarm intelligence in natural systems include ant colonies, bee colonies, bird flocking, hawks hunting, animal herding, bacterial growth, fish schooling and microbial intelligence. The application of swarm principles to robots is called swarm robotics, while swarm intelligence refers to the more general set of algorithms. Swarm prediction has been used in the context of forecasting problems. Similar approaches to those proposed for swarm robotics are considered for genetically modified organisms and synthetic collective intelligence. History. Artificial beings with intelligence appeared as storytelling devices in antiquity, and have been common in fiction, as in Mary Shelley's Frankenstein or Carol Apek's RUR. These characters and their fates raised many of the same issues now discussed in the ethics of artificial intelligence. The study of mechanical or formal reasoning began with philosophers and mathematicians in antiquity. The study of mathematical logic led directly to Alan Turing's theory of computation, which suggested that a machine, by shuffling symbols as simple as 0 and 1, could simulate any conceivable act of mathematical deduction. This insight that digital computers can simulate any process of formal reasoning is known as the Church-Turing thesis. This, along with concurrent discoveries in neurobiology, information theory, and cybernetics, led researchers to consider the possibility of building an electronic brain. The first work that is now generally recognized as AI was McLeod and Pitt's 1943 formal design for Turing-complete artificial neurons. By the 1950s, two visions for how to achieve machine intelligence emerged. One vision, known as symbolic AI or GOFAI, was to use computers to create a symbolic representation of the world and systems that could reason about the world. Proponents included Alan Newell, Herbert A. Simon, and Marvin Minsky. Closely associated with this approach was the heuristic search approach, which likened intelligence to a problem of exploring a space of possibilities for answers. The second vision, known as the connectionist approach, sought to achieve intelligence through learning. Proponents of this approach, most prominently Frank Rosenblatt, sought to connect perceptron in ways inspired by connections of neurons. James Menyika and others have compared the two approaches to the mind and the brain. Menyika argues that symbolic approaches dominated the push for artificial intelligence in this period, due in part to its connection to intellectual traditions of Descartes, Boole, Gottlob Frege, Bertrand Russell, and others. Connectionist approaches based on cybernetics or artificial neural networks were pushed to the background but have gained new prominence in recent decades. The field of AI research was born at a workshop at Dartmouth College in 1956. The attendees became the founders and leaders of AI research. They and their students produced programs that the press described as astonishing. Computers were learning checkers strategies, solving word problems in algebra, proving logical theorems and speaking English. By the middle of the 1960s, research in the U.S. was heavily funded by the Department of Defense, and laboratories had been established around the world. Researchers in the 1960s and the 1970s were convinced that symbolic approaches would eventually succeed in creating a machine with artificial general intelligence and considered this the goal of their field. Herbert Simon predicted, "Machines will be capable, within 20 years, of doing any work a man can do. Marvin Minsky agreed, writing, "Within a generation, the problem of creating artificial intelligence will substantially be solved." They had failed to recognize the difficulty of some of the remaining tasks. Progress slowed, and in 1974, in response to the criticism of Sir James Lighthill, and ongoing pressure from the U.S. Congress to fund more productive projects, both the U.S. and British governments cut off exploratory research in AI. The next few years would later be called an AI winter, a period when obtaining funding for AI projects was difficult. In the early 1980s, AI research was revived by the commercial success of expert systems, a form of AI program that simulated the knowledge and analytical skills of human experts. By 1985, the market for AI had reached over $1 billion. At the same time, Japan's fifth-generation computer project inspired the US and British governments to restore funding for academic research. However, beginning with the collapse of the Lisp machine market in 1987, AI once again fell into disrepute, and a second, longer-lasting winter began. Many researchers began to doubt that the symbolic approach would be able to imitate all the processes of human cognition, especially perception, robotics, learning and pattern recognition. A number of researchers began to look into subsymbolic approaches to specific AI problems. Robotics researchers, such as Rodney Brooks, rejected symbolic AI and focused on the basic engineering problems that would allow robots to move, survive, and learn their environment. Interest in neural networks and connectionism was revived by Geoffrey Hinton, David Rumelhart, and others in the middle of the 1980s. Soft computing tools were developed in the 1980s, such as neural networks, fuzzy systems, gray system theory, evolutionary computation, and many tools drawn from statistics or mathematical optimization. AI gradually restored its reputation in the late 1990s and early 21st century by finding specific solutions to specific problems. The narrow focus allowed researchers to produce verifiable results, exploit more mathematical methods, and collaborate with other fields. By 2000, solutions developed by AI researchers were being widely used, although in the 1990s they were rarely described as artificial intelligence. Faster computers, algorithmic improvements, and access to large amounts of data enabled advances in machine learning and perception. Data-hungry deep learning methods started to dominate accuracy benchmarks around 2012. According to Bloomberg's Jack Clark, 2015 was a landmark year for artificial intelligence, with the number of software projects that use AI within Google increased from a sporadic usage in 2012 to more than 2,700 projects. He attributes this to an increase in affordable neural networks, due to a rise in cloud computing infrastructure and to an increase in research tools and datasets. In a 2017 survey, 1 in 5 companies reported they had incorporated AI in some offerings or processes. The amount of research into AI increased by 50% in the years 2015-2019. Numerous academic researchers became concerned that AI was no longer pursuing the original goal of creating versatile, fully intelligent machines. Much of current research involves statistical AI, which is overwhelmingly used to solve specific problems, even highly successful techniques such as deep learning. This concern has led to the subfield of artificial general intelligence, which had several well-funded institutions by the 2010s. Goals. The general problem of simulating intelligence has been broken down into sub-problems. These consist of particular traits or capabilities that researchers expect an intelligent system to display. The traits described below have received the most attention. Reasoning, problem solving. Early researchers developed algorithms that imitated step-by-step reasoning that humans use when they solve puzzles or make logical deductions. By the late 1980s and 1990s, AI research had developed methods for dealing with uncertain or incomplete information, employing concepts from probability and economics. Many of these algorithms proved to be insufficient for solving large reasoning problems because they experienced a combinatorial explosion. They became exponentially slower as the problems grew larger. Even humans rarely use the step-by-step deduction that early AI research could model. They solve most of their problems using fast, intuitive judgments. Knowledge representation. Knowledge representation and knowledge engineering allow AI programs to answer questions intelligently and make deductions about real-world facts. A representation of what exists is an ontology, the set of objects, relations, concepts, and properties formally described so that software agents can interpret them. The most general ontologies are called upper ontologies, which attempt to provide a foundation for all other knowledge and act as mediators between domain ontologies that cover specific knowledge about a particular knowledge domain. A truly intelligent program would also need access to common sense knowledge, the set of facts that an average person knows. The semantics of an ontology is typically represented in description logic, such as the web ontology language. AI research has developed tools to represent specific domains, such as objects, properties, categories, and relations between objects. Situations, events, states, and time. Causes and effects. Knowledge about knowledge. Default reasoning. As well as other domains. Among the most difficult problems in AI are the breadth of common sense knowledge and the subsymbolic form of most common sense knowledge. Formal knowledge representations are used in content-based indexing and retrieval, scene interpretation, clinical decision support, knowledge discovery, and other areas. Planning. An intelligent agent that can plan makes a representation of the state of the world, makes predictions about how their actions will change it and make choices that maximize the utility of the available choices. In classical planning problems, the agent can assume that it is the only system acting in the world, allowing the agent to be certain of the consequences of its actions. However, if the agent is not the only actor, then it requires that the agent reason under uncertainty, and continuously reassess its environment and adapt. Multi-agent planning uses the cooperation and competition of many agents to achieve a given goal. Emergent behavior such as this is used by evolutionary algorithms and swarm intelligence. Learning. Machine learning, a fundamental concept of AI research since the field's inception, is the study of computer algorithms that improve automatically through experience. Unsupervised learning finds patterns in a stream of input. Supervised learning requires a human to label the input data first, and comes in two main varieties: classification and numerical regression. Classification is used to determine what category something belongs in. The program sees a number of examples of things from several categories and will learn to classify new inputs. Regression is the attempt to produce a function that describes the relationship between inputs and outputs and predicts how the outputs should change as the inputs change. Both classifiers and regression learners can be viewed as function approximators trying to learn an unknown function. For example, a spam classifier can be viewed as learning a function that maps from the text of an email to one of two categories, spam or not spam. In reinforcement learning, the agent is rewarded for good responses and punished for bad ones. The agent classifies its responses to form a strategy for operating in its problem space. Transfer learning is when the knowledge gained from one problem is applied to a new problem. Computational learning theory can assess learners by computational complexity, by sample complexity, or by other notions of optimization. Natural language processing. Natural language processing allows machines to read and understand human language. A sufficiently powerful natural language processing system would enable natural language user interfaces and the acquisition of knowledge directly from human written sources, such as newswire texts. Some straightforward applications of NLP include information retrieval, question answering and machine translation. Symbolic AI used formal syntax to translate the deep structure of sentences into logic. This failed to produce useful applications, due to the intractability of logic and the breadth of common sense knowledge. Modern statistical techniques include CO occurrence frequencies, keyword spotting, transformer-based deep learning, and others. They have achieved acceptable accuracy at the page or paragraph level, and, by 2019, could generate coherent text. Perception. Machine perception is the ability to use input from sensors to deduce aspects of the world. Applications include speech recognition, facial recognition, and object recognition. Computer vision is the ability to analyze visual input. Motion and manipulation. AI is heavily used in robotics. Localization is how a robot knows its location and maps its environment. When given a small, static, and visible environment, this is easy. However, dynamic environments, such as the interior of a patient's breathing body, pose a greater challenge. Motion planning is the process of breaking down a movement task into primitives such as individual joint movements. Such movement often involves compliant motion, a process where movement requires maintaining physical contact with an object. Robots can learn from experience how to move efficiently despite the presence of friction and gear slippage. Social intelligence. Effective computing is an interdisciplinary umbrella that comprises systems that recognize, interpret, process or simulate human feeling, emotion, and mood. For example, some virtual assistants are programmed to speak conversationally or even to banter humorously. It makes them appear more sensitive to the emotional dynamics of human interaction, or to otherwise facilitate human-computer interaction. However, this tends to give naive users an unrealistic conception of how intelligent existing computer agents actually are. Moderate successes related to effective computing include textual sentiment analysis and, more recently, multimodal sentiment analysis, wherein AI classifies the affects displayed by a videotape subject. General intelligence. A machine with general intelligence can solve a wide variety of problems with breadth and versatility similar to human intelligence. There are several competing ideas about how to develop artificial general intelligence. Hans Moravec and Marvin Minsky argue that work in different individual domains can be incorporated into an advanced multi-agent system or cognitive architecture with general intelligence. Pedro Domingos hopes that there is a conceptually straightforward, but mathematically difficult, master algorithm that could lead to AGI. Others believe that anthropomorphic features like an artificial brain or simulated child development will someday reach a critical point where general intelligence emerges. Tools. Search and optimization. AI can solve many problems by intelligently searching through many possible solutions. Reasoning can be reduced to performing a search. For example, logical proof can be viewed as searching for a path that leads from premises to conclusions, where each step is the application of an inference rule. Planning algorithms search through trees of goals and subgoals, attempting to find a path to a target goal, a process called means-ends analysis. Robotics algorithms for moving limbs and grasping objects use local searches in configuration space. Simple exhaustive searches are rarely sufficient for most real-world problems. The search space quickly grows to astronomical numbers. The result is a search that is too slow or never completes. The solution, for many problems, is to use heuristics or rules of thumb that prioritize choices in favor of those more likely to reach a goal and to do so in a shorter number of steps. In some search methodologies, heuristics can also serve to eliminate some choices unlikely to lead to a goal. Heuristics supply the program with a best guess for the path on which the solution lies. Heuristics limit the search for solutions into a smaller sample size. A very different kind of search came to prominence in the 1990s, based on the mathematical theory of optimization. For many problems, it is possible to begin the search with some form of a guess and then refine the guess incrementally until no more refinements can be made. These algorithms can be visualized as blind hill climbing. We begin the search at a random point on the landscape, and then, by jumps or steps, we keep moving our guess uphill, until we reach the top. Other related optimization algorithms include random optimization, beam search, and meta-heuristics like simulated annealing. Evolutionary computation uses a form of optimization search. For example, they may begin with a population of organisms and then allow them to mutate and recombine, selecting only the fittest to survive each generation. Classic evolutionary algorithms include genetic algorithms, gene expression programming, and genetic programming. Alternatively, distributed search processes can coordinate via swarm intelligence algorithms. Two popular swarm algorithms used in search are particle swarm optimization and ant colony optimization. Logic is used for knowledge representation and problem solving, but it can be applied to other problems as well. For example, the SAT-plan algorithm uses logic for planning. An inductive logic programming is a method for learning. Several different forms of logic are used in AI research. Propositional logic involves truth functions such as or and not. First-order logic adds quantifiers and predicates and can express facts about objects, their properties, and their relations with each other. Fuzzy logic assigns a degree of truth to vague statements such as "Alice is old," that are too linguistically imprecise to be completely true or false. Default logics, non-monotonic logics, and circumscription are forms of logic designed to help with default reasoning and the qualification problem. Several extensions of logic have been designed to handle specific domains of knowledge, such as description logics, situation calculus, event calculus, and fluent calculus, causal calculus, belief calculus, and modal logics. Logics to model contradictory or inconsistent statements arising in multi-agent systems have also been designed, such as paraconsistent logics. Probabilistic methods for uncertain reasoning. Many problems in AI require the agent to operate with incomplete or uncertain information. AI researchers have devised a number of tools to solve these problems using methods from probability theory and economics. Bayesian networks are a very general tool that can be used for various problems, including reasoning, learning, planning, and perception. Probabilistic algorithms can also be used for filtering, prediction, smoothing, and finding explanations for streams of data, helping perception systems to analyze processes that occur over time. A key concept from the science of economics is utility, a measure of how valuable something is to an intelligent agent. Precise mathematical tools have been developed that analyze how an agent can make choices and plan, using decision theory, decision analysis, and information value theory. These tools include models such as Markov decision processes, dynamic decision networks, game theory, and mechanism design. Classifiers and statistical learning methods. The simplest AI applications can be divided into two types: classifiers and controllers. Controllers do, however, also classify conditions before inferring actions, and therefore classification forms a central part of many AI systems. Classifiers are functions that use pattern matching to determine the closest match. They can be tuned according to examples, making them very attractive for use in AI. These examples are known as observations or patterns. In supervised learning, each pattern belongs to a certain predefined class. A class is a decision that has to be made. All the observations combined with their class labels are known as a data set. When a new observation is received, that observation is classified based on previous experience. A classifier can be trained in various ways, there are many statistical and machine learning approaches. The decision tree is the simplest and most widely used symbolic machine learning algorithm. K-nearest neighbor algorithm was the most widely used analogical AI until the mid-1990s. Kernel methods such as the support vector machine displaced K-nearest neighbor in the 1990s. The naive Bayes classifier is reportedly the most widely used learner at Google, due in part to its scalability. Neural networks are also used for classification. Classifier performance depends greatly on the characteristics of the data to be classified, such as the dataset size, distribution of samples across classes, dimensionality, and the level of noise. Model-based classifiers perform well if the assumed model is an extremely good fit for the actual data. Otherwise, if no matching model is available, and if accuracy is the sole concern, conventional wisdom is that discriminative classifiers tend to be more accurate than model-based classifiers such as naive Bayes on most practical data sets. Artificial neural networks. Neural networks were inspired by the architecture of neurons in the human brain. A simple neuron N accepts input from other neurons, each of which, when activated, casts a weighted vote for or against whether neuron N should itself activate. Learning requires an algorithm to adjust these weights based on the training data. One simple algorithm is to increase the weight between two connected neurons when the activation of one triggers the successful activation of another. Neurons have a continuous spectrum of activation. In addition, neurons can process inputs in a nonlinear way rather than weighing straightforward votes. Modern neural networks model complex relationships between inputs and outputs and find patterns in data. They can learn continuous functions and even digital logical operations. Neural networks can be viewed as a type of mathematical optimization. They perform gradient descent on a multidimensional topology that was created by training the network. The most common training technique is the backpropagation algorithm. Other learning techniques for neural networks are Hebbian learning, GMDH, or competitive learning. The main categories of networks are acyclic or feed-forward neural networks and recurrent neural networks. Among the most popular feed-forward networks are perceptrons, multilayer perceptrons, and radial basis networks. Deep learning. Specialized languages and hardware. Specialized languages for artificial intelligence have been developed, such as Lisp, Prolog, TensorFlow and many others. Hardware developed for AI includes AI accelerators and neuromorphic computing. Applications. AI is relevant to any intellectual task. Modern artificial intelligence techniques are pervasive and are too numerous to list here. Frequently, when a technique reaches mainstream use, it is no longer considered artificial intelligence. This phenomenon is described as the AI effect. In the 2010s, AI applications were at the heart of the most commercially successful areas of computing, and have become a ubiquitous feature of daily life. AI is used in search engines, targeting online advertisements, recommendation systems, driving internet traffic, targeted advertising, virtual assistants, autonomous vehicles, automatic language translation, facial recognition, image labeling, and spam filtering. There are also thousands of successful AI applications used to solve problems for specific industries or institutions. A few examples are energy storage, deepfakes, medical diagnosis, military logistics, or supply chain management. Game playing has been a test of AI's strength since the 1950s. Deep Blue became the first computer chess playing system to beat a reigning world chess champion, Garry Kasparov, on May 11, 1997. In 2011, in a Jeopardy! Quiz show exhibition match, IBM's question-answering system, Watson, defeated the two greatest Jeopardy! Champions, Brad Rutter and Ken Jennings, by a significant margin. In March 2016, AlphaGo won 4 out of 5 games of Go in a match with Go champion Lee Sedol, becoming the first computer Go playing system to beat a professional Go player without handicaps. Other programs handle imperfect information games, such as for poker at a superhuman level, Pluribus, and Cfuse. DeepMind in the 2010s developed a generalized artificial intelligence that could learn many diverse Atari games on its own. By 2020, natural language processing systems such as the enormous GPT-3 were matching human performance on pre-existing benchmarks, albeit without the system attaining a common-sense understanding of the contents of the benchmarks. DeepMind's AlphaFold 2 demonstrated the ability to approximate, in hours rather than months, the 3D structure of a protein. Other applications predict the result of judicial decisions, create art, and prove mathematical theorems. In 2019, WIPO reported that AI was the most prolific emerging technology in terms of number of patent applications and granted patents. The Internet of Things was estimated to be the largest in terms of market size. It was followed, again in market size, by big data technologies, robotics, AI, 3D printing, and the fifth generation of mobile services. Since AI emerged in the 1950s, 340,000 AI-related patent applications were filed by innovators and 1.6 million scientific papers have been published by researchers, with the majority of all AI-related patent filings published since 2013. Companies represent 26 out of the top 30 AI patent applicants, with universities or public research organizations accounting for the remaining 4. The ratio of scientific papers to inventions has significantly decreased from 8:1 in 2010 to 3:1 in 2016, which is attributed to be indicative of a shift from theoretical research to the use of AI technologies in commercial products and services. Machine learning is the dominant AI technique disclosed in patents and is included in more than 1/3 of all identified inventions, with computer vision being the most popular functional application. AI-related patents not only disclose AI techniques and applications, they often also refer to an application field or industry. 20 application fields were identified in 2016 and included, in order of magnitude, telecommunications, transportation, life and medical sciences, and personal devices, computing and human-computer interaction. Other sectors included banking, entertainment, security, industry and manufacturing, agriculture, and networks. IBM has the largest portfolio of AI patents with 8,290 patent applications, followed by Microsoft with 5,930 patent applications. Philosophy. Defining artificial intelligence. Alan Turing wrote in 1950, "I propose to consider the question, can machines think?" He advised changing the question from whether a machine thinks, to whether or not it is possible for machinery to show intelligent behavior. He devised the Turing test, which measures the ability of a machine to simulate human conversation. Oxford English Dictionary defines artificial intelligence as the theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. A definition that has also been adopted by Google, major practitioner in the field of AI, and other AI practitioners. This definition stipulated the ability of systems to synthesize information as the manifestation of intelligence, similar to the way it is defined in biological intelligence. It does not require a procedural action component, such as in many definitions of intelligent agents. Confusion with intelligent agents. Evaluating approaches to AI. No established unifying theory or paradigm has guided AI research for most of its history. The unprecedented success of statistical machine learning in the 2010s eclipsed all other approaches. This approach is mostly subsymbolic, neat, soft, and narrow. Critics argue that these questions may have to be revisited by future generations of AI researchers. Symbolic AI and its limits. Neat versus scruffy. Soft versus hard computing. Narrow versus general AI. Machine consciousness, sentience, and mind. The philosophy of mind does not know whether a machine can have a mind, consciousness, and mental states, in the same sense that human beings do. This issue considers the internal experiences of the machine, rather than its external behavior. Mainstream AI research considers this issue irrelevant because it does not affect the goals of the field. Stuart Russell and Peter Norvig observe that most AI researchers don't care about the as long as the program works, they don't care whether you call it a simulation of intelligence or real intelligence. However, the question has become central to the philosophy of mind. It is also typically the central question at issue in artificial intelligence in fiction. Consciousness. Computationalism and functionalism. Robot rights. Future. Superintelligence. A superintelligence, hyperintelligence, or superhuman intelligence, is a hypothetical agent that would possess intelligence far surpassing that of the brightest and most gifted human mind. Superintelligence may also refer to the form or degree of intelligence possessed by such an agent. If research into artificial general intelligence produced sufficiently intelligent software, it might be able to reprogram and improve itself. The improved software would be even better at improving itself, leading to recursive self-improvement. Its intelligence would increase exponentially in an intelligence explosion and could dramatically surpass humans. Science fiction writer Werner Ving named this scenario the singularity. Because it is difficult or impossible to know the limits of intelligence or the capabilities of superintelligent machines, the technological singularity is an occurrence beyond which events are unpredictable or even unfathomable. Robot designer Hans Moravec, cyberneticist Kevin Warwick, and inventor Ray Kurzweil have predicted that humans and machines will merge in the future into cyborgs that are more capable and powerful than either. This idea, called transhumanism, has roots in Aldous Huxley and Robert Edinger. Edward Fredkin argues that artificial intelligence is the next stage in evolution, an idea first proposed by Samuel Butler's Darwin Among the Machines as far back as 1863, and expanded upon by George Dyson in his book of the same name in 1998. Risks. Technological unemployment. Bad actors and weaponized AI. Algorithmic bias. Existential risk. Copyright. Ethical machines. Friendly AI are machines that have been designed from the beginning to minimize risks and to make choices that benefit humans. Eliezer Yudkowsky, who coined the term, argues that developing friendly AI should be a higher research priority. It may require a large investment and it must be completed before AI becomes an existential risk. Machines with intelligence have the potential to use their intelligence to make ethical decisions. The field of machine ethics provides machines with ethical principles and procedures for resolving ethical dilemmas. Machine ethics is also called machine morality, computational ethics, or computational morality, and was founded at an AAAI symposium in 2005. Other approaches include Wendell Wallach's Artificial Moral Agents and Stuart J. Russell's 3 Principles for Developing Provably Beneficial Machines. Regulation. The regulation of artificial intelligence is the development of public sector policies and laws for promoting and regulating artificial intelligence. It is therefore related to the broader regulation of algorithms. The regulatory and policy landscape for AI is an emerging issue in jurisdictions globally. Between 2016 and 2020, more than 30 countries adopted dedicated strategies for AI. Most EU member states had released national AI strategies, as had Canada, China, India, Japan, Mauritius, the Russian Federation, Saudi Arabia, United Arab Emirates, US and Vietnam. Others were in the process of elaborating their own AI strategy, including Bangladesh, Malaysia, and Tunisia. The Global Partnership on Artificial Intelligence was launched in June 2020, stating a need for AI to be developed in accordance with human rights and democratic values, to ensure public confidence and trust in the technology. Henry Kissinger, Eric Schmidt, and Daniel Huttenlocher published a joint statement in November 2021 calling for a government commission to regulate AI. In fiction, thought-capable artificial beings have appeared as storytelling devices since antiquity, and have been a persistent theme in science fiction. A common trope in these works began with Mary Shelley's Frankenstein, where a human creation becomes a threat to its masters. This includes such works as Arthur C. Clarke's and Stanley Kubrick's 2001, A Space Odyssey, with HAL 9000, the murderous computer in charge of the Discovery 1 spaceship, as well as The Terminator and The Matrix. In contrast, the rare loyal robots such as Gort from The Day the Earth Stood Still and Bishop from Aliens are less prominent in popular culture. Isaac Asimov introduced the 3 laws of robotics in many books and stories, most notably the Multivac series about a superintelligent computer of the same name. Asimov's laws are often brought up during lay discussions of machine ethics. While almost all artificial intelligence researchers are familiar with Asimov's laws through popular culture, they generally consider the laws useless for many reasons, one of which is their ambiguity. Transhumanism is explored in the manga Ghost in the Shell and the science fiction series Dune. Several works use AI to force us to confront the fundamental question of what makes us human, showing us artificial beings that have the ability to feel, and thus to suffer. This appears in Carol Apek's RUR, the film's AI Artificial Intelligence and Ex Machina, as well as the novel Do Androids Dream of Electric Sheep, by Philip K. Dick. Dick considers the idea that our understanding of human subjectivity is altered by technology created with artificial intelligence. Scientific diplomacy. Warfare. As technology and research evolve and the world enters the third revolution of warfare following gunpowder and nuclear weapons, the artificial intelligence arms race ensues between the United States, China, and Russia, 3 countries with the world's top 5 highest military budgets. Intentions of being a world leader in AI research by 2030 have been declared by China's leader Xi Jinping, and President Putin of Russia has stated that whoever becomes the leader in this sphere will become the ruler of the world. If Russia were to become the leader in AI research, President Putin has stated Russia's intent to share some of their research with the world so as to not monopolize the field, similar to their current sharing of nuclear technologies, maintaining science diplomacy relations. The United States, China, and Russia are some examples of countries that have taken their stances toward military artificial intelligence since as early as 2014, having established military programs to develop cyber weapons, control lethal autonomous weapons, and drones that can be used for surveillance. Russo-Ukrainian War. Warfare regulations. Cybersecurity. With the ever-evolving cyber attacks and generation of devices, AI can be used for threat detection and more effective response by risk prioritization. With this tool, some challenges are also presented such as privacy, informed consent, and responsible use. According to CISA, the cyberspace is difficult to secure for the following factors: the ability of malicious actors to operate from anywhere in the world, the linkages between cyberspace and physical systems, and the difficulty of reducing vulnerabilities and consequences in complex cyber networks. With the increased technological advances of the world, the risk for wide-scale consequential events rises. Paradoxically, the ability to protect information and create a line of communication between the scientific and diplomatic community thrives. The role of cybersecurity in diplomacy has become increasingly relevant, creating the term of cyber diplomacy, which is not uniformly defined and not synonymous with cyber defense. Many nations have developed unique approaches to scientific diplomacy in cyberspace. Czech Republic's approach, Germany's approach, European Union's approach, Russo-Ukrainian war, election security. As artificial intelligence grows and the overwhelming amount of news portrayed through cyberspace expands, it is becoming extremely overwhelming for a voter to know what to believe. There are many intelligent codes, referred to as bots, written to portray people on social media with the goal of spreading misinformation. The 2016 U.S. election is a victim of such actions. During the Hillary Clinton and Donald Trump campaign, artificial intelligent bots from Russia were spreading misinformation about the candidates in order to help the Trump campaign. Analysts concluded that approximately 19% of Twitter tweets centered around the 2016 election were detected to come from bots. YouTube in recent years has been used to spread political information as well. Although there is no proof that the platform attempts to manipulate its viewers' opinions, YouTube's AI algorithm recommends videos of similar variety. If a person begins to research right-wing political podcasts, then YouTube's algorithm will recommend more right-wing videos. The uprising in a program called deepfake, a software used to replicate someone's face and words, has also shown its potential threat. In 2018, a deepfake video of Barack Obama was released saying words he claims to have never said. While in a national election a deepfake will quickly be debunked, the software has the capability to heavily sway a smaller local election. This tool holds a lot of potential for spreading misinformation and is monitored with great attention. Although it may be seen as a tool used for harm, AI can help enhance election campaigns as well. AI bots can be programmed to target articles with known misinformation. The bots can then indicate what is being misinformed to help shine light on the truth. AI can also be used to inform a person where each part stands on a certain topic such as healthcare or climate change. The political leaders of a nation have heavy sway on international affairs. Thus, a political leader with a lack of interest for international collaborative scientific advancement can have a negative impact in the scientific diplomacy of that nation. Future of work. Facial recognition. AI in school. AI in medicine. AI in business. Business and diplomacy. AI in foreign policy. Multiple nations around the globe employ artificial intelligence to assist with their foreign policy decisions. The Chinese Department of External Security Affairs under the Ministry of Foreign Affairs uses AI to review almost all its foreign investment projects for risk mitigation. The government of China plans to utilize artificial intelligence in its $900 billion Global Infrastructure Development Plan, called the Belt and Road Initiative for Political, Economic, and Environmental Risk Alleviation. Over 200 applications of artificial intelligence are being used by over 46 United Nations agencies, in sectors ranging from healthcare dealing with issues such as combating COVID-19 to smart agriculture, to assist the UN in political and diplomatic relations. One example is the use of AI by the UN Global Pulse program to model the effect of the spread of COVID-19 on internally displaced people and refugee settlements to assist them in creating an appropriate global health policy. Novel AI tools such as remote sensing can also be employed by diplomats for collecting and analyzing data and near real-time tracking of objects such as troop or refugee movements along borders in violent conflict zones. Artificial intelligence can be used to mitigate vital cross-national diplomatic talks to prevent translation errors caused by human translators. A major example is the 2021 Anchorage meetings held between US and China aimed at stabilizing foreign relations, only for it to have the opposite effect, increasing tension and aggressiveness between the two nations, due to translation errors caused by human translators. In the meeting, when United States National Security Advisor to President Joe Biden, Jacob Jeremiah Sullivan stated, "We do not seek conflict, but we welcome stiff competition and we will always stand up for our principles, for our people, and for our friends. It was mistranslated into Chinese as "we will face competition between us, and will present our stance in a very clear manner," adding an aggressive tone to the speech. AI's ability for fast and efficient natural language processing and real-time translation and transliteration makes it an important tool for foreign policy communication between nations and prevents unintended mistranslation. See also: AI rising, AI control problem, artificial intelligence arms race, artificial philosophy, behavior selection algorithm, business process automation, case-based reasoning, emergent algorithm, female gendering of AI technologies, glossary of artificial intelligence, robotic process automation, synthetic intelligence, universal basic income, weak AI, operations research, explanatory notes, citations, references, attribution. This article incorporates text from a free content work. Licensed under C by SA 3.0 IGO. Text taken from UNESCO Science Report, The Race Against Time for Smarter Development, Schneegans, S. T. Straza and J. Lewis, UNESCO. To learn how to add open license text to Wikipedia articles, please see this how-to page. For information on reusing text from Wikipedia, please see the terms of use. AI textbooks. These were the 4 most widely used AI textbooks in 2008.